Good morning, Auto 2. We're going to be talking about ignition system components this morning. In the overview, we did look at components, but albeit very quickly. So we're going to take a more in-depth look at all of our different ignition system components. I want to remind you that I'm going to be talking fast, probably faster than normal. So you might want to put your YouTube speed at like 0.75. If you don't know how to change the speed, let me know and I'll show you how on the computer. Or you can pause, whatever, but make sure you take notes on this. Okay, here we go. So first is the ignition switch. And what we have with the ignition switch is an ignition feed circuit. When we say feed, we're talking about battery power or battery positive power. So we've got some voltage supplied to the ignition system coil by the battery, approximately 12 volts during cranking. You guys know that cranking voltage usually drops to somewhere between 10 and 11 volts. We generically say 12 volts, but it's really like if you measure the voltage at the coil during cranking, it's going to be starting system voltage approximately 10 to 11 volts. Once the car starts, the voltage supplied by the alternator to the coil is going to be somewhere between 13.5, 14.5, maybe as high as 15. And we call this the primary circuit. So this is all low voltage. So all the components with low voltage going through them are part of the primary circuit. So an ignition switch, we've got a key operated switch or we've got a push button switch. We're going to supply power to the primary windings. Again, during cranking, we say through a bypass circuit for easier starting. On some systems, we don't put full battery voltage to the coil when we're running, but on all cars that I've seen, we use a bypass circuit, so we do get full battery voltage during starting to make sure the spark is as hot as possible. So then many cars, once they start, we supply power to the coil indirectly through a resistance circuit, meaning we cut the voltage down, let's say from 14 volts from the alternator to maybe on some systems as low as 5 or 6 volts. I'm not going to go into all the reasons for that, but in old school speak, we used to do that with points because it would keep them from arcing. But lots of cars, we just give direct or full charging system voltage to the coil now. And that's kind of the norm as far as I've seen. So a bypass circuit, all it's showing is that there's going to the coil, there may be through the ignition system a resistor, but during cranking we just bypass that so we get full battery voltage to the coil. So then here's the resistance circuit. So when the car is running, then it would go through this resistor and chop the voltage down. This one's showing down from 14.5 to 10 volts. And you say, why do I need to know this? Well, because if you're checking voltage at a coil on a car that's not it's a crank no start or something, you want to know, is the voltage there correct? Is there something else wrong, assuming you've already checked out the battery and the charging system, made sure that's correct. So let's talk about ignition coil. So ignition coil is a step-up transformer. We're going to boost the voltage from charging system voltage, again, approximately 14 volts, up to like 10,000 volts. So we can jump the gap between the center and side electrode on that spark plug when the engine's running to ignite our air and fuel. Obviously, we're boosting our voltage, like I just said, and old systems would run like 4,000 to 8,000 volts, especially at idle. And newer systems will usually idle anywhere from 7,000 to 10,000 volts. They'll go up higher, 30,000, 40,000 volts under heavy load, accelerating up the requested grade, etc., etc. Both of these happen to be DIS or Coil Pack ignition coils. This is 3 pairs of coils firing 6 cylinders. This is 1 coil firing 2 cylinders. So the ignition coil windings, the primary windings, which I was showing you yesterday, are several hundred turns of fairly heavy wire wrapped around usually the secondary, whereas the secondary is several thousand turns of almost hair-like wire. And what we typically do is we're going to put that right up inside there like that. And so that's how every coil is constructed. Well, having said that, I'll walk away and grab a more modern coil that I've cut in half so you can see it. This one there's the primary windings in the center, and there's the secondary. Sorry, you can't see the canyon. Primary windings here, secondary here. So what they've done is they've wrapped it. I sliced through this coil down the center, so all you're seeing was what looks like 2 lines. Sorry, here and here. But that's actually a loop that was cut through, and then these 2 look like two lines, and that's a loop. So this one is injection molded plastic right around that coil, and so on. Okay, here we go. So there's an iron core, and it's a segmented iron bars, and I'll grab one right here so you can see what they look like. These are the iron bars that go down the center of that primary and secondary coil winding, and that's going to concentrate the magnetic field so that that step-up transformer does a better job. Here we go. So there's a picture of an ignition coil, and the primary windings are out here, and the secondary windings. Not really a good picture because you really can't see the difference between them, but you can see the segmented iron bars going down the center. And obviously this is an old school single can type coil that actually even looks like a transformer on a power pole that you're used to seeing as you walk down your neighborhood. If you're not got your head in your cell phone, wow. Let's keep going. So here's an ignition coil picture showing the primary and secondary wrapped around an iron core. Obviously in this schematic it doesn't really look actual because the primary windings would be several hundred of heavy wire, and this would be thousands of turns of very fine wire. But that's a symbol showing the iron core. Let's keep going. So coil operation, current flows through the primary winding, and when it does, it's going to make a magnetic field. Anytime you put electricity through a conductor, you get magnetism around it. If you wrap that, it gets stronger. If you put segmented iron bars down it, it gets even stronger. So what it's going to say here is the iron core helps to concentrate it, and when current is interrupted, the magnetic field collapses. We use the word collapses. We don't say ceases to exist because it doesn't just instantly like go away, but as the coil current flow turns off in this primary winding, when you turn it off, the magnetism basically goes out and affects the primary windings, or sorry, the secondary winding. This one's showing a secondary winding wrapped around that piece of like cardboard, and again, I don't think you can see it in the camera, but it is like very fine hair-like wire, and I'm going to see if it'll, yeah, there it's focusing when it's on my hand there. You can see that little stuff that looks like hair coming off the top. It's extremely delicate little copper single strand wire, and you can get as much as 60,000 volts. There's a Ford out there that makes 100,000 volts out of the coil. We say that to define a term, dwell is the primary current on time, meaning when the 14 volts is going through the primary windings, we call that the on time of the coil, and we call that dwell. So dwell is the on time of the primary winding current flow. Coil saturation just means that when the coil is completely filled with magnetism, we say it's saturated, like you'd saturate a sponge. Okay? And so this picture is just showing that the primary dwell period is when the current flow is flowing through and the switching circuit's closed and we're going to ground. We're making a magnetic field. That's primary dwell period, or that's the current on time, or primary, or the dwell on time. Dwell ends when we disrupt the path to ground, so current can no longer flow through the primary windings to ground. So when we disrupt this, it stops flowing. Magnetism is no longer being built up, and we get a collapse of the magnetic field and a high voltage surge into the secondary, and we say it collapses across the secondary windings, causing a boost in the secondary windings. So let's talk about designs of coils. Okay, so a conventional coil, what we used to call a conventional, was a single can type coil. It was one coil for all cylinders. It had a non-conductive cooling oil in it, and these did not fail very often, once in a while. Then we have DIS. I'm going to grab one over here. You can't see me for a moment, but here's a DIS coil. That's this one coil is feeding two cylinders. So you got, I'm sorry, it's feeding it's actually two coils. One coil here, feeding two cylinders there and two cylinders there. So it kind of looks like that's probably a Subaru. Yep, that's what it is. That's a Subaru coil. So, and they're solid. They don't have oil in them. And then a direct ignition coil, or a coil on plug coil, again, is like this. And I'll bring it over here. It's a little easier to see. We call it COP. We have one coil for each cylinder, and it's a solid coil, meaning there's no non-conductive oil cooling it inside. So coils back in the day when they had that non-conductive oil and they were can-type coils, they didn't fail very often. These do fail. Now we find these do fail. They don't have the oil in there. They're cheaper to manufacture this way. And what kills coils is people don't service their plugs. The side to center electrode contact gets really, really wide. The coil has to make more and more voltage to fire it, and I find that eventually that causes the coil to go bad. So a coil pack is several coils. This would be for an 8-cylinder. Each of these coils firing 2 cylinders each. Okay. And so on waste spark ignition coil, again, just being a little repetitive, it fires 2 plugs at the same time. I already said that. Each end of the coil's secondary winding is connected to a plug, and we had a good picture of that yesterday. High voltage forces current flow through 2 wires firing each plug with opposite polarity. That means one jumps from center to side terminal, and the other one jumps from side to center terminal. And the engine grounds the 2 spark plugs. We call this DIS or distributorless, and I want to remind you that there is no useful purpose for having a spark during the exhaust stroke of a cylinder. It's other than the design is very simple to wire up that way. We don't need a spark during the exhaust stroke. It doesn't help to reduce emissions or anything like that, no matter what you might think. Okay. The ignition control module is our next component, and its responsibility is to turn on and off the coil primary current flow. Again, so the ignition module's job, and here's an ignition module for a GM vehicle. The job of this ignition module, which is essentially a transistor, which is a fully electronic on-off switch, its job is to turn the current flow on and off in this primary coil. When we go on, we make magnetism. When we go off, we get a high voltage surge into the secondary because that magnetism collapses. This is another style of GM divorced coil module. This is inside the distributor of every Suburban and pickup truck from like 1986 to about 1994. Okay, let's keep going. It says ignition coils can be remote mounted in the engine compartment, meaning separate over on the fender. They can be on the side of the distributor, they can be inside the distributor, and they can be inside the PCM. So the oldest modules typically were in the distributor, then on the distributor, then on the fender, and then many of them now inside the PCM. So remember, PCM is powertrain control module. That's the engine computer. So this is just going to show some pictures. Sorry, let me go back. So this is just showing pictures of where the modules are. There's one, a GM one that was inside the distributor. There's a Ford one that was on the side of the distributor. There's one that was on fender mounted, and those are actually both fender mounted. I'm looking to see if I have one on the side of a distributor so I can show you. I do not, but here's a GM one where the module is, which is our primary current flow switching device, is right inside the distributor. So you can see the distributor shaft there. Here's also, I don't have any others here where I can show you a module in a distributor or on a distributor. Let's talk about module operation. So it says as a trigger wheel approaches a pickup, and this is the pickup right here. As this wheel, these teeth come around and approach that pickup, voltage turns the module transistor on. So what happens is, as one of these teeth comes by this pickup, which is a permanent magnet, current flow will start flowing in that module in one direction. When it lines up, it actually stops flowing, and when it moves away, it flows the opposite direction. So this thing is a little AC voltage generator, and I need to see if I can make that any more. See if I can get that thing to do a better job of focusing, but it doesn't seem like I can. This is a pictorial right here of an ignition module. A module is a transistor where it has a base, emitter, collector. So this little magnetic pickup is sending voltage into that base. I'm going to pause and see if I can get this more focused. One sec. All right, well, that's about the best that I can do to get that focused. So again, the point of this triggering device is to energize the base of the transistor, which makes it conductive, and then that allows battery power to flow through the primary windings of the coil through the transistor to ground. And remember, when you put current through primary windings of the coil, you make magnetism and so on. Next, so when the trigger wheel passes, I thought it was going to show it. It's okay. Let's look at the text. When the trigger wheel passes the pickup coil, it turns the transistor off. Primary current flow stops flowing, and magnetism collapses, inducing high voltage in the secondary, causing a spark. I'm going to show this to you. I'm very aware that I'm going too fast, and I'm counting on you to pause if you need to. So as this trigger wheel goes away from that magnetic pickup, it no longer gives voltage to the base. The transistor becomes non-conductive. Current flow can't flow through the transistor to ground. The magnetic field collapses and causes a high voltage surge, which in this case, a single can coil goes through a distributor to a rotating rotor and then to a spark plug. Again, this is old school because we don't have distributors and single can coils anymore, but it's pretty simple to see. Here's a little more modern GM distributor with its module. Okay, here's our ignition coil with the primary windings and secondary windings. This module is being triggered by this pickup. So this is energizing the base of the transistor, which allows current to flow through the primary windings, or it's de-energizing the base of the transistor and shutting the coil off. So let's talk a little bit about triggering devices. So it's a device that's used to energize the base of a transistor. So here's another type of transistor. This one's a Ford transistor. Again, an on-off switch. Here's a 98 Honda Civic. This is, I can give you a little size comparison. Here's kind of the old school ones that were fender mounted and how big they were compared. Now they're all really, really small. And again, a lot of modern cars are now inside the PCM, but these little devices are going to energize the base of a transistor. So we call this a triggering device. This makes the base of the transistor conductive. I probably should add base there. Current's going to flow through the primary windings of the coil when the transistor is conductive. And again, we call that dwell time. And let's keep going. So here's some types of triggering devices. And we'll talk about these: magnetic pickup, Hall effect, optical. These two are a little bit older, and this is kind of seems to be what most everything is. Most everybody's doing it now off their crankshaft position sensor, which is typically a magnetic pickup. General Motors had a Hall effect one for a while. So a magnetic pickup reluctor wheel, called a reluctor or pole piece. I'm going to show this to you. It's fastened to the distributor. So again, this is kind of old school, but here's an old Ford electronic ignition distributor, and here's the reluctor, which has these poles, one for each cylinder. So this is a V8. There's the magnetic pickup triggering device. The module is separate from this distributor. So let's keep going here. So the pickup coil is a small set of windings from a coil, and there's a permanent magnet in there. And I don't know that I would take notes down on this because it's what I've already been saying. Trigger wheel tooth passes the pickup coil, changing the magnetic field, and you get an induced AC voltage to the base of that transistor. Sorry, that needs to be fixed. So here's a toothed wheel, and this one's lined up with that magnetic pickup, and this one's moved away from it. So they're just kind of showing you how that works. I'm going to go pretty fast now. A Hall effect is another type of transistor that energizes the base of another type of triggering device to energize the base of a transistor. It's a solid state chip. It produces a signal when triggered by a slotted wheel, and constant voltage is applied to the device. So this was a Chrysler one, and this Hall effect had a metal vein that went down through there, and this guy sent a signal to the module base. And it's got a permanent magnet. On these, I really don't need you to take notes on these so much because, in fact, I'm just going to fly through this because here you go. Here's a Hall effect here because I just want to expose you to it. So there's a metal vein that goes down between these two components. We call it a Hall. One's a permanent magnet and one's got a pickup in there. Okay. And so it's just kind of showing you how this thing's laid out. An optical one actually uses light emitting diodes. I'm just going to show it to you to shoot through a slot. So these were light emitting diodes that went down through this plate, and there were slots in the plate, and believe it or not, we would be able to generate a little voltage to energize the base of a module transistor. And again, I'm going too fast now on purpose because you don't need to take notes on all those specifics. So I'm going next to an ignition distributor, which is a device, if you have a distributor, and this is old school, these were gone on most cars, or the latest model car, Honda Civic 2001. It had a rotating shaft, usually driven off the camshaft, and it had a rotor spinning. And that rotor, which I'm going to show you right now, there's a rotor. And here's a General Motors distributor cap. This isn't the right one for this cap, but as that spun around, spark electricity would come down through the center of the rotor, jump off the tip, jump to these side terminals that you can see up in there, and then go out the top through a spark plug wire to a spark plug. Okay. And again, I'm going to recommend that you don't necessarily take notes on this, but you just kind of listen. So distributor functions, we're going to control the on-off cycle of the coil primary. We're going to distribute high voltage spark to the correct spark plug in order. And we're going to control timing in relation to speed and load. Speed meaning engine speed, and load meaning how much force against the vehicle, like are we going up a hill, etc. And many of them would drive the oil pump. And it might also have the ignition coil in it and an electronic switching circuit, meaning the module. So this is a Toyota one where you had, here's a distributor, it's got a rotor in it, that's the coil, there's the pickup, and there's the module. So everything for this ignition system is in this distributor. Here's a GM HEI, I think I have one sitting here. What did I do with it? It's right in front of me, nope, right behind me. This is a GM HEI, it's a complete ignition system. Inside this guy is a distributor. It drives the shaft driven off the camshaft, and it drives the oil pump there. And this guy has an ignition coil in it, has a module, has a pickup. This is an entire ignition system. All you have to do is have spark plug wires going out of this to the spark plugs. Okay. Let's keep going here. A couple of distributor types. Please don't write anything down on this. Old school contact points, more modern with a magnetic pickup or a Hall effect or an optical. So this is kind of Ford, this was kind of Chrysler, this was kind of Honda, and this was also kind of General Motors, things like that. Let's keep going here. That's just showing the rotor and the cap and how the rotor spins and spark electricity goes out of the coil. This actually has a spring-loaded carbon button, and this guy rotates, and there is a gap between the rotor tip and the side electrode, so you actually get a spark there, so those will wear out over time, and then you get the spark at the spark plug. Just showing a cap and rotor, insulated plastic cap. The center terminal is going to touch the rotor delivering spark. The spark is going to jump the gap from rotor to side terminals in the firing order. Side terminals are carrying current to the wire and plugs. I'm giving too much on this because this is, at this point, super old, but hey, it's all right. Cap and rotor problems just shows how you can break a terminal, or you can get what's called a carbon trace, and it'll fire to the wrong cylinder. There's another one there. Okay. So let's talk about plug wires. So plug wires are still valid because we still have them on many cars, or several cars. So they can carry current produced by the ignition coil. They are a resistant type of wire, so we don't mess with your radio. So you don't mess with your radio reception. It has a fiber down the center that's essentially like fiberglass, and it does have a maximum resistance of 1,000 ohms per inch, etc. Okay, so we're going to clip them through on this GM cap. This would be General Motors Vortec, like I think it's 94 up to, sorry. I think it's 96 up until 2004. And I think I have one of those right here. Let me look really quick. I don't have one handy. I do have one over on the rack over there. So this had a separate, we call it a GM HEI, EST. HEI was high energy ignition. EST was electronic spark timing. And we call this one a divorce coil because the coil is separate from the distributor. That's all those GM Vortex. It's just showing how the wire is constructed on the inside. Talk a little bit about spark plugs. So spark plugs are going to take that high voltage and provide essentially a terminal for the spark to jump from the side to the center on this very, very worn out spark plug here. I think I can get it to focus for you if I put my hand in front of it. Yep, there it is. You can see that center electrode is almost worn down to where you can't even see it in the porcelain. So it's really, really worn out. Okay. And let's keep going here. So 4,000, 20,000. This is old school. Everything's like 7,000 to 10,000 at idle. And spark plug types. So resistor and non-resistor. These days, as far as I know, everything's got a resistor in it. So if you take an ohm meter and you touch here, and you touch here, you'll usually get like 5,000 ohms of resistance. There's some that actually have a gap, and you'll get open circuit if you check them. This just shows different types of designs of spark plugs. So in this slide, you see different types of spark plugs, different types of diameters, 14 mil, 18 mil. This is a 14 mil, this is a 14 mil. This is a long reach, this is a short reach. These two are what we call tapered seed plugs. These are gasketed plugs. The most common one is a 14 mil long reach with a gasketed, sometimes short. You won't see these too much anymore. Spark plugs did have heat range, and that just was the distance that the heat would travel to where it could dissipate into the engine block. It's kind of a thing of the past, but we would run a hotter plug on an engine that was burning oil because it would tend to keep it from fouling. Fouling means that it sort of bridges the gap between the side and center electrode with oil. This just shows that on a short insulator, it has a shorter path to get cooled, and this one has a longer path to get cooled. So this is the hot plug, this is the cold plug. And the reason why they might use a colder plug is if they have a car that's detonating or something like that. So when we go ahead and service spark plugs, when we lack power or rough starting or bad fuel economy, the tips get coated with ash or oil or deposited from fuel additives. The electrodes burn and the gap gets very wide, like I showed you on the one just a little bit ago. And we can use an oscilloscope or a QV tester to see how much voltage they're putting out, or we usually just remove it and we just measure the gap between that side and the center electrode with a spark plug gapper. I think it's going to come up here in just a moment. On a modern car, we really depend on the misfire codes, P0300 codes, P0301, misfire cylinder 1, P0308, misfire cylinder 8, to help us diagnose a misfire. So this is just showing a normal plug where the center electrode, which is made out of iron, and sometimes it has a platinum tip on it, and a side electrode made out of iron, sometimes with a platinum tip, going to the threads. Conventionally, the spark will jump from the center to the side and go to ground through the threads in the cylinder head. And if it's a DIS, some of them are reverse polarity where they go from the side terminal to the center terminal. Here's a oil-fouled plug where it's got about oily deposits on it. This could be because of worn rings, valve seals. There's one that has, this says ash fouled, and that's fuel deposits on there, making all that crusty stuff on that side electrode. Looks like moss. A carbon fouled, like our rich air-filled mixtures, would be a dry sooty, and this one had preignition and it was actually damaging that guy. And this is normal wear, but this is really worn. When you see a center electrode sloping off like that, you definitely want to change those plugs before you hurt the coil. You might see a buildup there. But that one's definitely old, and it's too old. It should have been replaced before that. A couple things about firing orders. So the firing order is the sequence in which the spark plugs fire. So typical firing order for a 4-cylinder is 1-4-3-2 or 1-3-4-2, something like that. What we're trying to do is we're trying to offset the power pulses so the engine doesn't vibrate end to end or side to side if it's a V6 or V8. Sometimes there's a cast into the intake manifold, you'll see that number. But we use this if we're installing spark plug wires, if we have them, or different things like that, or if we need to know if the scan tool says we got a P0304, which is cylinder 4 misfire, which cylinder is cylinder 4. Well, we can go to ProDemand, and in fact, I'll do that right now. So if you pause there for a moment, let me take this away, and hopefully you can hear me. And I'm going to open up ProDemand, and we'll go to I've got a 2004. I'm going to log into ProDemand. And I've got a 2004 Toyota Tundra. And I'm going to go ahead, and it's got a 3.4 V6. It's a base model. It's a standard transmission. I'm going to put use this vehicle. And then what I'm going to do is I'm going to go to service manual, and if I click on engine performance right there, and under specs, it should say firing order and cylinder identification. There it is. And mine's a V6. There it is. So what you're seeing on the screen here is they're saying the front of the engine is this way, and you know that means this is a longitudinal engine. That's where the belts are. That means that the driver's side cylinders are 246, and the passenger side are 135. So if I had a PO304, it's a misfire on the middle cylinder on the driver's bank. Okay, let's keep going here. Let me go back to the PowerPoint. Okay, so next will be, this is just showing, I guess it could have just gone here, but I wanted to show you where it was on ProDemand. This is showing a 4-cylinder with its firing order, 6-cylinder, a V8. All three of these engines are showing distributors, so they're all very old, and they're showing the rotation of the distributor. This is a 1, 5, 6, 3, 4, 2, 7, 8 is the firing order, for example. There's a distributorless ignition firing order. Okay, so we've got different coils, and it shows how they're wired up. And that's it. Awesome.